In this video, we're going to look at the systematic approach for solving differential equations. So we have seen how to split up the domain and do several pieces for a standard function. But now we're going to look at how to actually solve differential equations systematically and piecewise. But first, let's look at the systematic approach and what that entails. So we have been solving differential equations using the Galerkin method by just stating the Galerkin method the same way we have done since lecture 1. Now we will look at how to actually do this programmatically, more efficiently in a computer, because the previous approach works very well if you're doing it by hand, but as I said countless times, this method is not really about doing things by hand, it's about doing things in a computer. So we need to prepare the problem mathematically to serve it to a computer to solve more efficiently. So we will take a look at this model problem, this very simple differential equation, second order differential equation here, using very simple boundary conditions. In the next video, I will show you how to handle more general boundary conditions, more complex boundary conditions. But now we need to start somewhere simple, because there's so many concepts that we need to touch upon, and this vastness, this vast amount of new knowledge is just going to be overwhelming if it isn't already. So we'll take things in baby steps. So let's look at the weak form. So this is the weak form for this problem, and you have already derived this earlier. We'll call this one weak form. And now when we have the weak form, we use the approximation, and we shall approximate this using one linear element. So our approximation is going to look like this. We will have two basis functions, because this is what makes up our approximation for the whole region. So this is really in yeah, I can say it like this, in which is 1 to 3, so in this region. Alright, and given this, the general form of our basis functions are going to be that. So given that we are doing this using linear elements, this sets the game rules, if you want, so that our basis function is then of course a linear basis function, and this is the general form of for a linear basis function. Alright, we have the basis function. Now how about the derivative of u, because we need to approximate this guy here as well. So that is going to be not that, it's going to be so the derivative of u is approximated using capital U here, the derivative of capital U, which is the derivative of course, this whole approximation here. And we can now break out the derivative here. We can take, because ui is not varying with x, it's the basis function. This is just a constant, it's a coefficient. So the actual derivative is going to be applied on our basis function. So du dx is simplified to d phi dx times ui on this format. Okay, so we have the we have this approximation of the derivative, and our v, our test function, is just going to be replaced using Galerkin with the actual basis function. So that's Galerkin here, replacing v with phi. Alright, we insert the approximation into our weak form here, and we end up with this. So we're just replacing it 1 to 1. So this summation is of course attached to this here, so we could really, we should really say that. I'm using sort of Einstein summation here because I'm as lazy as he was. That's probably the only features we two share. But yeah, so this is the summation index. So if there's no sum explicitly like this, you can see that if there's an index I and there's another index I here, that means that these are summed together for different i's. So this stuff here is the same as this stuff here. I wasn't lazy when I wrote this, but I was here. So yeah, so this is the u dx, and then we have the phi dx here. And note that we are summing over I, right? So this here will ultimately become a scalar, and then this scalar is then multiplied by a vector, essentially, because you know we have two of these phi values here, and we have two derivatives. So we're multiplying this with phi1 and with phi2, or rather the derivatives of phi1 and phi2. And this is all equal to this other integral over here, where we have phi j as well. So these are the same, j in the indices, and of course j is also included here, which is our boundary. Okay, so now what we're doing is we're going to move the summation out of here. So we will move, well, rather we'll move I out of this. All right, so this will lead to this expression here. So we're moving I out of the integral sign, and we're still summing over this. So this is still the same operation. So we're summing over all of this stuff here, but this now becomes actually a matrix. This becomes a matrix where each row is I and each column is, no, the other way around, where each row is j and each column is I. So this should really be the other way around. It's okay, and this is of course j as well, and then yeah. All right, so yeah, so this integral here becomes a matrix because we're sort of, and I will show you how this looks on matrix notation later, but for now this index notation will suffice. And all of this is then summed using ui. So this is ultimately the same as this here, but we can now express this as a matrix multiplying a vector ui, and this is equal to another vector. And this will also become a vector because we can call these two values that we get, these two terms, we can call them g1 and g2, and this index here denotes which node they belong to. So the force boundary condition are expanded. We will expand this g business here to show you. So we have this, and this is of course expanded to this, and then we identify g2, which is the upper bound, as this, and g1, which is the lower bound. Now note here that I'm actually including this negative sign, so g1 will always be negative, or rather it will always have this negative sign attached. I mean, the actual value can also be negative, then this whole thing becomes positive, so it's dependent on what the actual value here is, but it has a negative sign attached to it. Don't forget that. Okay, so this business here will of course lead to a system of equations. So we will get this. So this matrix here, if we do the summation, this will get S11 times U1 plus S12 times U2 is equal to F1 minus G1, right? Minus because this thing is, there's a minus sign there. And then the other one will be S21 times U1 plus S22 times U2 equal to F2 plus G2, right? This thing is positive. Yeah, you don't need to mind the basis functions because they will always be evaluated to 1 in its node and 0 in the other. So that means that essentially if you just work it out, you can do that if you want. I'm not going to do it here, but you can work it out and you will see that this thing is always going to be 1. So it's, I mean, the basis function will always be 1. So this is always going to be valid. And only for the endpoints. The basis function is actually what will cause this stuff here to be 0 everywhere else except in the actual boundaries. In the actual boundaries, this thing will be 1, and we will get 2 values here. And again, I'll get it's okay if you don't grasp this perfectly now. I'll get back to this later. All right, so because we have this equation system, of course, we can express this as a matrix, and that's really what we should do. So this thing on matrix form is just, well, we have this thing called S, this S matrix. Sometimes that's called the system matrix, but if you're coming from sort of what's it called, mechanical engineering, if you're doing static analysis, then this mechanical analysis, then this is the stiffness matrix, because there is a way of deriving all of these equations using there are two analogies. So one is the one I have chosen to teach you, which is this thing where you just take any differential equation and you multiply it with a test function and you integrate over the whole domain, and then you do, of course, partial integrals to get out the to break things down into manageable quantities, such as these here, where you don't have higher order differences. But the other approach of deriving all of these equations really stems from the physical idea that you have a potential, because you're sort of saying that, all right, we have forces, and these forces can cause, well, energies. We have potential energies, and you're minimizing this energy. So this whole method is called, this approach is called the minimization of the potential energy. And that approach it's a subset of this other approach, because this other approach is always valid. You can always take any differential equation, be it a ordinary differential equation, partial differential equation, time, whatever, and you can always multiply it with the test function and integrate over the area, and you will sort of derive a weak form which you can work with and apply an approximation using Galerkin if you want, or any other approximation types. There are many of them. You can do Laplacians, you can do many things. Anyhow, this other approach is from the sort of mechanical engineering side, if you want, which deals with energies and something called virtual displacements. And that approach is what they do in textbooks, standard textbooks, is they work with springs. So you will always see a system of springs. It's like two springs, and each spring has, of course, a spring stiffness. And if you take two springs and you put them in series, and you say that, okay, the leftmost spring, the node, if you want, the leftmost node, is attached to a wall, and then you insert a force on the rightmost node, and you pull it apart, and the problem becomes, okay, what are the two nodes? What is the end node and what is the middle node? And you can solve this using finite element method, and that's how actually this whole thing is derived in many textbooks. And that's why this matrix that sort of gets created from that viewpoint is called the stiffness matrix, because it's nothing else but stiffness. It's the stiffness. It's all of these springs combined into a stiffness. And a more general term, I don't really like the term stiffness matrix, because even if the finite element method is mostly used, in our profession at least, to do structural analysis, it's not only used for that. It's used for heat. It's used for wave propagation. It's used for many different things. It's used for fluid dynamics. There's so many things that the finite element method is good at, as well as the finite difference method, really, which also has system matrices, and the finite volume method, and so on. So there's many different methods which use this type. You will always get some matrix multiplying a solution field, and which is going to be equal to some other load vector. And what we usually call them, we denote them with S or K in textbooks, and we call them system matrices. So you have it. It's either, so this whole lengthy discussion really comes down to that this is called a system matrix or the stiffness matrix. And this is your solution vector, and this is called the load vector, or just the left-hand side, really. That's what we usually call it. We call it just the left-hand side. Right. Now, obviously, we cannot solve this yet because we haven't really applied any boundary conditions. So we need to sort of reduce it. So we have boundary conditions here. We will apply these. These are boundary conditions. And if you look at the solution first, we have u of 0 is equal to 0. So we call that it's the first node u1, it's equal to 0, right? So this thing here is equal to 0. So we can sort of set this to 0 because we know what it should be 0. That means that none of this here, this business, so what is going to be multiplying u1? Well, it's going to be s11. So this thing here is going to be multiplying this, and this is going to be, so the whole row here is not going to be interesting for our solution. And the whole row and the whole column here, s21, because this is also multiplying this thing here. So we can get rid of this. You can say that row 1 and column 1, those rows and columns that are tied to our solution, which is known, are eliminated from the equation system. They do not contribute to the solution. Then we have the du dx of 3 is equal to 0, so that means that g2, this guy here, is equal to 0. So that is also known. So what we can say that, alright, so this thing here is known, it's supposed to be 0, and we're not removing that. That is known now. So that means that, alright, we have S22, we have F2, and we can solve for U2 here, because this other stuff here is going to be eliminated. We just cross it out, because the solution at that row and that column is known. That is important. And we end up with the following. We have this equation, which we can easily solve. So this is like an easy introduction to this whole systematic approach when we deal with solutions on matrix form, like this. All right, moving on. Now we're looking at the systematic approach with piecewise approximation for differential equations. So if you just look at the figure from the previous problem here, we have an approximation using 4 linear elements. And this solution is, of course, piecewise. So it's a piecewise linear solution or approximation. We are splitting the domain into n elements. And as we do that, we can approach the true solution, the exact solution, as the number of elements approaches infinity. In practice, we will never do that. That's infeasible. That's not the point of this approximation. N is in practice going to be much less than infinity. It's it's for any typical problem, an industrial size problem, N is usually in the range, if you have high fidelity, if you want it to be very accurate, let's say it's around 1 million. Oh, that order of magnitude at least. So it's very far away from infinite, but we're interested in just getting a good approximation with respect to time and the complexity of the model. Because if we increase n, our solution time will increase as well. And it's not linear. This thing can be exponential, so it's very expensive. And also, the accuracy will increase with n, but we have other things that we can affect the accuracy. So it's not just, hey, you know what, we will get extreme good solutions if we just increase the number of elements here. Usually not. There's other assumptions that we're making that can affect our accuracy much more. So we need to keep that in mind. All right, now, what will we do with this? How will we approach this systematic approach? Well, we need to take a look at the actual mesh. So typical element that we have is going to be defined between two nodes in 1D. So one element is defined as this entity that lies between two nodes. So xi and xj. There are two nodes next to each other, and E is defined as the element between xi and xj, and this is also a element that contributes only to equations I and j. So if you're looking at this as a system of equations, we have the equation I and its neighbor j, then one element will only affect these two equations. For example, element 2 here in this example mesh, if we take a look at this mesh with the corresponding linear basis functions, then we can see here that we have, for every element, we have a basis function, which is the well, two basis functions if they're linear, so we denote them as a vector, and they have a valid region which is in for this element, so they're valid for this element only. And a little bit overlapping here, so they're sort of meeting each other at the nodes, but they are contributing to this overall stiffness matrix that we have, to this equation system. So we have the contributions of the element stiffness matrix for the second element here that looks like this. So our stiffness matrix, our element stiffness matrix, so we will have a contribution from every element into our global stiffness matrix, the global stiffness matrix, which affects all of these the whole mesh. We have the contribution from every single element stiffness matrix here. So we have two things. We have two matrices. We have the global stiffness matrix, this whole thing here, and we have local stiffness matrices that are coming from each element. And this is what we're looking at. We're looking at the element stiffness matrix for element number 2, which is this guy here. And we're looking at, okay, what which nodes does this affect? Well, it affects nodes 2 and 3. And not just nodes, but also equations 2 and 3. So that means that this thing here, this integral, will yield this element matrix, which sort of fits into these places in our global stiffness matrix. And we can compute all of these. We can compute the stiffness for the place 2, 2. That's the second row and second column. This is the second row and third column. And I'll get to the graphical explanation soon. But we can compute all of these. It's the same range. We're going from x2 to x3 over this range here. But our basis functions are going to change slightly here. So for 2, 2 here, we have basis function 2 and basis multiplying basis function 2. Here we have 2 multiplying 3, 3 multiplying 2, 3 multiplying 3 for these. This is the logic that governs this. Now we can take a look at the complete stiffness matrix to see where this is going to fit in. So this is our complete stiffness matrix. And we have a 5 by 5 matrix here because we have 5 nodes, 5 degrees of freedom. And this guy between nodes 2 and 3 is of course contributing to this place here. So at the degrees of freedom 2 and 2 we have S22, and then at 2, 3 we have 2, 3. So the numbers are corresponding to the global stiffness matrix here. Now, in order for this to make more sense when we're dealing with this, we need to do a local numbering, really, because it's kind of hard to keep track of what basis functions will go where globally. So what we will do is just a variable substitution. We will call phi1 always our first local basis function. So for every element, we have two basis functions. We have phi1 and phi2. And these are corresponding to phi I and phi j in the global, but we're just going to call them phi1 and phi2 for every. And we're going to define these for every element. So phi1 and phi2 will be unique for every element. They will be dependent on, of course, our coordinates here. And the coordinates for every element will, of course, also be x1 and x2, but they are corresponding to the global nodes xi and xj. So thus the element stiffness matrix will become just the following. We will have SE here denoting our element stiffness matrix, and they will have the local coordinates x1 and x2, which will vary for every element, and they will be multiplying these differentials here with our basis functions phi1 and phi1 in this place, phi1, phi2 in this place, phi2, phi1 here, and phi2, phi2 in the 2, 2 position down here, following this logic here. So the same way, the load vector is also going to be a element load vector using local numberings 1 and 2 here for phi1 and phi2. Now we will look at the assembly process. So assembly is when we have computed this per element, where do we put this. So for every element we go in, and we're maybe in the second element now, so we have x1 be we have x1 equal to globally x2, and we have x2 equal to globally x3. So this is our current element, and we have computed this element mass matrix by doing all of this stuff here. Where do we put it in the global element matrix? So where here does it go? So we can see here where we should put it, but we need to have this process be more defined. So this is called the assembly process, and I'll show you this graphically. So for each element E, we add the element stiffness matrix and element load vector in the correct places in the global stiffness matrix S and global load vector F. So we have all of these positions, so where do we put stuff in? So for element 1, they will go here. They will go into these places. And again, we can see where they're supposed to go by just looking at the node number here. We have 1 and 2, so that means 1 1 1 2 2 1 and 2 2. So then once we have sort of stored the first element in this position, we move on to the second element. So that goes here then in the position 2 2 2 3 3 2 and 3 3, and we're adding on top of this. We're assembling stuff. So that means we don't overwrite this here, which is sort of overlapping. We're adding stiffness to it. So this becomes more. It becomes stiffer in a sense. And then we go on with the third and fourth element, like so. So we're adding stuff to this now in the third 3 3 position, 3 4 4 3 and 4 4 position, and finally in the 4 4 4 5 5 4 and 5 5 position here. And again, this position here is governed by where our element is. So element 4 is of course between x4 and x5, so between equation number 4 and 5. So this is this area here. This is the simplest way of looking at this. Connectivity, such as this that we're looking at, how one mesh is created or connected to another, can be much more complex. It can look in 2D more complex, because then we can mix elements. We can have in 2D general, we can have triangles, we can have quadrilaterals, we can have even lines connecting each other. So that this connectivity here, it's very straightforward in this case, but it can be a little bit more complex in general in 2 dimensions. And I'll get back to that when we get to that. So this assembly process, now as you have seen it graphically, it can be expressed sort of programmatically in this way. So we have SII new equal to S old II, and then we add our stiffness matrix SE11 to this. And for IJ, we have the old IJ, we have the new IJ, and we add 1 2 to that, and so on for the rest of the 4. And for the load vector, it's well simpler, because we just have 2 things. We have F new I equal to F old I, and then we add the first component of our element load vector to that. And for the other, we just have the other one at position J. All right. Let's copy this picture in here again, just to have it sort of close by, and we will take a look at the contributions from element 1. So the contributions mathematically from element 1 will be, of course, in this region here. So we have 1 2. So S at 1 2 comma 1 2, that's a 2 by 2 matrix, is going to be the old one here, plus the new stuff, the new element mass, or the new stiffness element stiffness matrix, which is a 2 by 2. Okay, and again it looks like this. We have this new element stiffness matrix here added to this new this global stiffness matrix here, and this white space here is just zeros. So that's the contribution from element 1. Now the contribution from element 2 is then going to be this. We have for element 2, we are here 2 3. So 2 3 2 3 in those positions, those sort of that's selecting which sort of area, which nodes, or which degrees of freedom we are accessing, and we're putting this element stiffness matrix in there, which is this which is denoted with the superscript 2. That's our element stiffness matrix from the second element, and this is from the first element, and they're overlapping in this 2,2 node here. So we're getting this accumulation of stiffness in that region. And then we just continue on using the same system to do this. And this is more complicated to sort of show intuitively like this. It's actually much easier if you just do this by hand, or even if you do it in Matlab, it's even more easy. So traditionally, when we didn't do this in Matlab, we've been doing this by hand in 2 dimensions. And I can show you that in the next lecture, how that is done, at least the 1D by hand. We'll solve a problem by hand completely. Now, we will take a look at an example to implement this stuff in Matlab using 4 linear elements. So, we will take a look at this same problem, and we'll apply exactly the same boundary conditions, but now we're going to use 4 linear elements. This will be a piecewise linear solution. We derive the weak form, and we just put it here because we have done that a couple of times now, and then we look at the approximation. So first, this test function here is replaced with our basis function that's gonna lurk in there, and we will, for linear elements, this basis function of course looks like this in the general form. So for any x1 and x2, then we have our actual solution approximation here, like so. And now I want to do this operation here as a vector operation. So I'm taking the basis function's vector and I'm multiplying it with the solution vector, which is a well, I could really do this in 2 ways. I can say that this is a scalar product by doing c dot here, or by just removing it and saying that, right, this thing is a row vector and this is a column vector, and this operation here will yield a scalar product. And that's why my preferred way, because that natively that's how Matlab does it. So after a while you will just get used to thinking vector operations everywhere. So depending on how you multiply 2 vectors, you will either get a scalar or you will get a outer product, which then of course yields a matrix. And we will do that with the actual stiffness matrix, so that's coming up next. For the differential or the derivative of u, we are approximating that using our approximation here, which of course is this summation here using the derivative of the basis functions. And this also is the same as taking the vector, the differential of the vector of the basis functions as a vector, and multiplying that by the column vector. So this is a row vector multiplying a column vector, and of course this will yield a scalar. Okay, we have the approximations. We put that into the weak form, and we will get this in the first step. So we're just throwing the stuff in there like so, and this other one is going to be there. We're just transposing that, and I'll get back to y because it needs to make mathematical sense, and that's why we need to transpose it, because we will get rid of u here now. We'll pull that out. And we also have a column vector here, and we have a column vector here. Okay, now we're doing this operation. Yeah, so this thing yields this here. So we have, now we take u and move it out, and then we need to switch these around. So we're putting the transpose first, because then we have a column vector multiplying a row vector, and this will yield a matrix. And this will be our stiffness matrix. And this is the same as we have a stiffness matrix multiplying u, and that's equal to this row column vector here, load vector, and the this g vector here. And this thing will have the same size as everything else, but it will just be full of zeros except in the boundaries, which is of course our first and last node or degree of freedom. Alright, so let's take a look at that last piece again, just to make certain that we understand it. So this thing is of course just this difference right? But we are attaching basis functions to this, which will make this be 1 only at the boundaries and 0 everywhere else. Alright, now let's take a look at this per element. So per element, for every element, we have the element stiffness matrix here. Which is nothing but this stuff here. It's just that this is on general, going from 1 to 3, and now we're in elements. So for in each element we have x1 and x2. And we have this guy here, which we need to implement in Matlab. And we have the element load vector here, like so, again going from x1 to x2. And on matrix, using 4 elements, which will yield 5 degrees of freedom, we have this thing here. So we have our stiffness matrix, just denoting with S here, and we have our solutions U1 to U5, and this is equal to F1 to F5. And now this G business, this is how it looks like, because these here, these basis functions, will guarantee that these are only 1 in the boundaries and 0 everywhere else. So this is what we end up with. Okay, now it's time to look at the actual boundary conditions. So our boundary conditions, U1 is equal to 0 and the UDX at 3 is equal to 0. So it's always very nice to do this graphically. So we have our mesh here with our solutions. So at x1 we have U1, x2 we have U2, and so on. Alright, and then we take a look at our system completely like this, and we just insert what we know. So okay, at U1, that's here, at 0, x1 is equal to 0, that means that U at 1 is equal to U1, so this guy here is equal to 0. So U1 is equal to U of 0 is equal to 0. This is what we know, this is the solution boundary value. How about this here, the force boundary value, the UDX? Well, at this position here, this is our the far right position, that's at U5 or X5 rather, and this is corresponding to G2. This is the last thing here. So this guy is known, the UDX of 3, and it's equal to, well, there's a parenthesis too much here, get rid of that, and that's equal to 0. So these are 2 boundary conditions which we have dealt with now. Alright, so far so good. This is what you need to sort of do by hand, just on paper, just to make sure that you understand where you're gonna put these guys here. And of course, be careful about this negative sign here. That's the typical mistake people making, forgetting this negative sign. But now we have this done, so we can implement this in Matlab. So the implementation, we're just gonna do n is equal to 4. Those are elements. And we're going to create our nodes x node here using the same stuff we've been doing before. So these are going to be linearly spaced between 1 and 3, and there's going to be n plus 1 nodes. So we can verify that this is correct. And there we go. 1, 2, 3. We have 5 of these. So I'm just gonna suppress this. And then we need to create our nodes. So this is the connectivity, telling us how each element is connected to each other. So this is going from 1 to n, and we're going to transpose that. And right next to it, we will have 2 to 2 until n plus 1. And we need to transpose this, so I need to put this in parentheses and transpose it. And let's take a look at that. So our first element is nodes 1 and 2, second element is nodes 2 and 3, and so on. So this looks reasonable. Can suppress that. Then we have the number of nodes. So number of node is equal to length of x node. And I can just write it out. This is going to be 5, yes, no surprise there. Moving on, I have the number of equations. Number of equation is going to be the same as the number of nodes because I have 1 degree of freedom. So I can just multiply this with 1 because I have 1 degree of freedom. And this will not change. We will not be doing any solution for 2D or 3D, probably, yeah, most likely. Yeah, so now I can create my stiffness matrix, I can pre-allocate it. So I'm just gonna create a matrix with a bunch of zeros here that is of the length of number of equations times number of equations. So yeah, so this 5 by 5 matrix, and the load vector is going to be F, and that's going to be a column vector. So we have 5 rows and 1 column, like so. All right, now in order to deal with the basis function, we haven't gone into how to do numerical integration yet, so we need to still deal with symbolics here. And this is the big elephant in the room, which we will get rid of in about 2 lectures. So we need the symbolic expression, symbolic variable x, a, and b, and then we will create our sort of template basis function here, phi of x, a, and b, and this is going to be equal to, and I'm just going to copy stuff in here now because I have a cheat sheet. There you go. So this is a linear thing which I've seen earlier as well, so we can just type that out and see that you recognize this. All right, now we can evaluate this for every element, and we will get a unique basis function for each element. Okay, time for the main thing, which is the for loop. So for IEL is equal to 1 to n, we can type out which element we are in, like that. And I suggest you just type out everything when n is low, so you can see what is happening. And then we have our nodes, our local nodes, IEL, EL, and then we're grabbing both of these. So this colon here means grab both, or grab everything which is in there, which is just 2 things. Next, coordinates xc, going to be x node, I nodes, like so, and then we have x1, the first of our coordinates, and x2, the second of our coordinates. And if I did quadratic implementation now, then I would keep track of which ones I'm using here, because I have 1, 2, 3. Yeah, you get it. Good. Now I can implement the basis function. So I'm using capital phi here, and it's still going to vary with x, but between x1 and x2. So this is my basis function for each element. So far so good. The thing I need to do now is to take the derivative out of my basis function. So d phi is going to be the differential of phi with respect to x. So this is my, and of course this is phi is linear, so the derivative will of course be a constant. Okay, now up until this point you're sort of following, but now what's the next step? So we will implement this now. So we have d phi here, we will transpose that and multiply it with itself, and then we'll see what we'll get. So we'll do that in steps. We can take d phi and we transpose it and we multiply it with d phi, and you see here you get this matrix, right? And if I didn't transpose it, I will of course get an error because the dimensions do not match, right? You can do this in your head, you can realize this doesn't work. If I transpose it wrong, then I will just get a scalar, and that's wrong. It needs to be a matrix. So this guy here will be transposed and I will get a matrix. All right. So once I have that, I can say that, okay, my element stiffness matrix SE is going to be the integral of this stuff here, like so, with respect to x from x1 to x2. And that's this integral. You can work this out by hand if you want. It's not a difficult integral to do. So moving on, we have the element load vector now, which is going to be the integral of phi times 1 if you want, just to make sort of sure that this is what you're doing. It's dependent on x from x1 to x2. Now guys, I'll let you know something here. I accidentally put d phi in here and I had to troubleshoot this for over an hour because I just was sure that this was correct. But then I found out that it actually there was this D in front of it, which sort of screwed it up. So yeah, everybody can make mistakes, and like nobody's gonna help you unless you're sitting, several heads in front of the computer, and making sure that what your type is, what you mean. So it happens to all of us. Sometimes you can find it quickly, and sometimes you can't. It gets frustrating, and that's the reality of computation. So you just need to spend time and figure out where the error is. Right. Okay, so now what we're doing is we're doing this assembly business, because we have these matrices and we need to put them in their corresponding place. And we go back and we look at how that is done. So we can sort of see it here, or we can see it here. I prefer this method because this stuff here, these vectors, are nothing but our inodes. So take a look, 1, 2, 2, 3. Let's take a look at the inodes. Inodes here is what? 1, 2, and then 2, 3. So exactly that. So our assembly process is just going to be take this S, which is just empty because we haven't inserted anything, and we're going to say that, all right, at these places inode S, inodes, at these places we're going to take what is already there, and we're going to add to this our element stiffness matrix. And we can see how this gets populated with a bunch of numbers. So in this case, we have 2, minus 2, minus 2, 2. And then, of course, in here, these are the overlapping values, and are going to be 4. In this particular case with n is equal to 4. This will change. Then we have our load vector, and that's inodes. And this is equal to f of inodes plus fe. So yeah, right, this thing needs to be transposed, right? So you're transposing phi here, and bam, this is what we have. We will always get a column vector in f here. Good. So our column vector is being populated, right? And we never know if this is correct until we actually plot this at the very end and see what's happening. That's the only indication if we've done things correct or wrong. All right, moving on. Now we can handle the actual boundary conditions here. So we have our stiffness matrix. We have, well, just a bunch of zeros here, really. And we have, or we haven't really created our solution vector, so this is not, that doesn't exist yet. We have our load vector, and we don't have the G vector. We will create that now. So we will start with just writing that we're now applying boundary conditions. So apply boundary conditions. Right. So I will start by saying, okay, I have all nodes. I have this vector with all the nodes, like so. These are all of my nodes. 1, 2 nodes. Why is nodes not defined? Because it's not that. I mean number of nodes. There we go. Number of nodes. This is 5, so I have 1, 2, 3, 4, 5. Here, I have all of them. Good. Then I will define which ones are prescribed. So prescribed u, the u's, the values of u. Which one of these is prescribed? It's not 2, it's not 3, it's not 4, it's not 5. It's 1. So 1 is prescribed. So this is a vector, but in this case I just have one of them being prescribed. So in general it is a vector, but now I just have one, so I just write 1. So that's this node here, really. But if I want, because I mean, let's say that the last one is defined, and how do I find the last one? That's why I use all nodes. So I use all nodes and then say the first one or the last one, end here. So if I do end, it's not end, but I can show you now. It's not the 5th in this case, it's the 1st, but I'm just showing you. If it was the last, then I would use end here. So it's a very nice way of not hard coding stuff. So I don't need to look at how big is n, how many nodes do I have. Oh yeah, it's supposed to be 5th one, and then just hard code it like this. That's one way of avoiding hard coding. So I can just put, all right, all nodes end if I mean the last one, because I can use it. So that's one way of guaranteeing that this is robust, because you want to put in as little time as possible, and you want to change your model later. So that's why you're sort of making this programmatically robust, so you can change stuff around without needing to go to 10 or 15 places and changing stuff which affects it, because that is prone to bugs. If you need to change stuff around in several places, you will forget something, you will get weird errors, and then you need to spend hours of time to find these. Trust me, I've been there. You will probably also get there, so don't worry. You will join my club of frustration soon enough. Now, we have our free nodes. Those are the ones that we can solve for. And those nodes are all other nodes than the prescribed nodes. And there's a way of defining that. We will set difference diff. So if you have a vector with the numbers 1, 2, 3, 4, 5, and you want to get all other vectors but the number 5, then you can set difference like this. You can write, this is your complete vector here, and you want to remove presc nodes from that. Presc u. So this is what you will get. You will get everything but the first one. So that's a very sort of nice programmatic way of getting that. Okay. Now that we have sort of stated what is known, or which nodes are known and which are unknown, I'm saying nodes here, but what I really mean is the degrees of freedom. But at this problem in one dimension, they are interchangeable. We have only 1 degree of freedom per node. So yeah, when I'm saying nodes, I really mean degrees of freedom. So we have the prescribed degrees of freedom, we have the prescribed, we have the free degrees of freedom, the ones that will actually make up our equation system. Now we can define this g vector here. So we'll just set it to a bunch of zeros for now. So first it's zeros, nec 1, same as with the load vector we've done before. And then we can say what is known. Well, we know that g at the first position here, which is all nodes 1, is so I can just do it like this. This thing here is supposed to be -0. So this is very redundant to write, I know, but I'm just making the point that I know that this is supposed to be 0 and whatever value g1 has. And currently g1 is 0. But if if this problem was stated differently, that this was 1, I would just change it here to 1. Or if it was -1, I would actually write it like this, just to really point out that sort of I know what I'm doing, and I expect you to do the same. Otherwise bugs, and if you can show to me that you understand something, then I have no idea what grade to award you. So be overly explicit. And the last one, end, is, well, it's just 0. We don't know it, so we won't really need to set it. So it's just, we just write stuff that we know here. Okay. Now we can call both of these. So this vector and this vector can be called something, and we can call it capital F. So we have F plus G. Of course, G is not affecting our solution in any way, it's just a bunch of zeros, but it's still there. All right. And in this very simple case where U is 0, it's not affecting our solution, but it actually it would be if U was anything else. I'll get to that in the next video because it's too many things at once. So I'll get to that later. So what I'm going to do now is I'm going to create U as just a bunch of zeros here. Again, this is redundant, so I have a bunch of zeros, and I'm going to take the one that I know, I'm going to set that to a value that I know, and it's 0 here. So again, really redundant, but I'm doing it anyway just to show you. Okay, so I have now inserted everything that is known. Now I can solve the system. So I can do U free. So for every other node except the first node, this is I'm going to solve the system, and I'm going to do S free and S free. So essentially, what I'm doing here is I'm grabbing all of these. So I'm grabbing this system matrix here from node 2, 2 here until node 5, 5. And this is going to be a new matrix. So this essentially is going to look something like this. The actual solution. It's going to be a 4 by 4. This is my new equation system. It's what we call a reduced equation system because we have removed all of the known solution rows and columns from this. And this is what I'm going to solve. If I try to solve the complete one, I will fail. But if I solve this, it will actually give me solutions. And these solutions will be populated in U3. So in all of these 4 points here, I will get a solution. All right, so I do this with the backslash operator, right? Because I don't solve I don't invert this or anything like that. I solve it the proper way. And 3 here as well. And I run this, and my solution thus becomes this. Now, when you're doing this on paper, now basically you're done. You have no way of verifying if this is correct or not, but we have computers, so we have so much more tools and computational power. So we can visualize these results. So I will just copy in the complete true solution in here. So we will have UE. So we're sort of creating UE because we don't want to mess up our U here. And this is our differential operator, the differential of UE, and we're taking derivative 2 times, setting this to 1. This is our du, and we have our boundary conditions here, and we're solving this, just sending on off the E and BC to desolve. We get this thing. We don't really need to do VPA on it or anything like that, so I can just get rid of it. We just want to plot it in our domain, which is 1, 2, 3 here. This is our true solution, and then we're just going to do hold on. And we're going to plot. Now we can't do fplot, we have to do plot our x and y coordinates, x node and u, and we're going to put markers and connect them with straight lines and make them blue. And this is what we get. So apparently this is alright, I would say. There's nothing messed up here. Of course, if you mess up something, for instance, now we can spend a little bit of time and just look what happens if you just try to do this for all. So if you just do S and F here, what will happen? Well, really what will happen is the matrix is close to singular or badly scaled, results may be inaccurate, and you get nothing back. And this is because this system is overdefined. You have to reduce it. You cannot do this. Yeah, it just doesn't make algebraic sense to do it this way. And if you want to know why exactly what happens and stuff like that, take a course in linear algebra, an advanced course, and you will find out. And what happens if you mess up? Let's say we make the same mistake I did. Let's say we put d phi here. That's exactly the mistake I made, which caused me like 1 hour of debugging. I got this. Obviously wrong. Obviously. So you find out your mistake, you fix it, and your solution will look okay. Of course, now we haven't programmed this not to just like do this. We of course want to go back now to the beginning here and increase this to like 8 nodes at least, and look at the solution. And there we go, beautifully. And let's go back to 2 solutions to get the same problem we had, or 2 solutions, 2 elements here, or even 1 element and 1. And there we go. Now we can take a look at U here. It's 2. Yeah, and you can verify this all the way in the beginning of this video. But yeah, essentially this is the systematic approach using a piecewise approximation, linear approximation in this case. And I'll get to how to do this quadratically later. because we need to fix the mesh before we get there. Yeah. But right, so this is what you have. If you want to give it a try now, since you've seen this video and you feel like, so because I haven't really produced the other videos, if you want to give it a try and see how this will work using quadratic approximation, be my guest, try it out. I know some of you are probably eager to do this. So if you have a bunch of time, do it. Otherwise, I'll get to it later. All right, perfect. That's it. In the next video, we will look at how to get rid of this dependency on integral here. This is the big elephant in the room. In order to get rid of this integration sign here, we need to really find out a way of numerically integrating functions. And we will see that this is quite hard if the region is always changing like it is here. So we will find a way of always having the local elements be in the region 0 to 1. And that is done by isoparametric mapping. And once we have done that in the next video, in the video after that, we will look at the actual numerical integration. And then we have a full 1D finite element solver created from scratch. All right. I look forward to getting the whole picture across. And yeah, study hard. See you in the next video. Bye.